Okay, so last time, right, I went over and we just kind of went over the test benches and how to write assert statements and that kind of thing. There is something that I want to point out for project 1, right, which we're hopefully all finishing this time. The night class actually did a really good job. I think I had 80% of students finish everything except the report, like the write-up, but they got all of the work done. And the remaining 20% were all testing. They all got to the test bench. And because the night class, they're on a weird schedule, and so they've had a couple of rough issues. You guys are actually kind of better off than they are. So I'm optimistic for your guys' success on project 1 today. So the first thing that I want to point out on project 1 is that you're going to write a test bench, and you're going to have 4 different test values and 5 different opcodes to test. Okay, and so when we get in there today in lab, I'm going to show you how to write embedded for loops. So far I taught a for loop. We can write for loops that are for something or something. And so for each iteration of this for loop will run through all of its choices. So this one would be 0 to 3, and this one would be 0 to 4. And then I would run a total of 4 times 5 options for 20 total loops. So we're going to start out that. If you're ahead and you're about ready to start writing your test bench for the complete ALU at the beginning of class, talk to me at the beginning of lab so that I can run through this, because otherwise I'm going to wait for like an hour into lab to teach this. But I do want you guys to know that there's a good way to run the test for this ALU involving for loops, assert statements, and constants. Okay, but today's new stuff, what did we talk about last time besides this? We didn't get into latches yet, right? No one knows what a latch is, or did we?
Yeah, finished on the JK flip-flop.
Oh, we finished on the JK flip-flop. Excellent, absolutely wonderful. So let me jump to that section of the JK flip-flop. And let's run over just a little bit of review first of latches and flip-flops, right? So latches are still fundamentally combinational devices, right? And the easiest way that I showed to build a latch was with the NOR gates. And we did this cross coupling. We called one set and one reset, right? And this we called Q, because if I set the value, Q will become 1. If I reset, Q will become 0. If they're both 0, Q will just stay whatever it used to be. And if I assert both, I break the circuit and unpredictable behavior happens. Then we wrote the symbol. And now we have an SR latch. And then we can combine the SR latch with a little bit of AND gate logic right at the input. And we can get a D latch. The D latch being something that just latches onto whatever the data value is, right? So if data is 1, it's 1, data 0, it's 0. It can optionally have something like, say, this would be an active low reset that would reset it back to 0, whatever, regardless of what data is doing, power it down. Then I can combine some of those and get a DQ flip-flop, where the DQ flip-flop has this little flag looking icon, which means this is a clock pin, right? This is an input for a clock. And the clocks, I ran through the timing last time on, right, on why we can use 2 of those to make a D flip-flop. And flip-flops are nice because now they give us the ability to synchronize our devices, right? Because the rising edge will happen at the same time across the whole device, and now the behaviors are synchronous. This makes synchronous logic. Then once I have this, I went and introduced the, let's just stay over here. I don't need to keep all of them. A few alternatives, right? The first one being the JK flip-flop, whose truth table looks like so, has J input, a K input. And we're going to talk about it in terms of time, right? What happens next? So this is Q at n plus 1, n being the number of Qs that had happened before. So maybe this is 100, and so the next one is 101, right? Or 0, and the next one is 1. With the JK saying 0, 0, stay the same, right? Which is very similar to what the set reset does, right? Which is just, if I don't set or reset, remember what you were before. 1 and 1, however, says do the opposite of that. Invert your value. And these other ones are reset and set. Okay. The JK flip-flop, it shows you in figure 12-34 if you want to go see how they're like actually built. But let's talk about the VHDL, right? How would we write a JK flip-flop? So I'm going to write this starting from the process, right? I'm not going to write the architecture, and I'm going to skip a few things going forward. You guys are getting to the point where you're hopefully starting to get a little bit comfortable with VHDL. If you're frustrated and confused with VHDL, don't worry, it's normal, right? Engineering is a lot of frustration and confusion as you slowly learn through new topics that are different than anything you've learned before. The only way to really learn is just go through it. So let's look at the process. So a process means that it's now sequential logic. One thing happens and then the next thing happens. In the test bench, right, we never had to worry about what we call the sensitivity list. But once we're trying to design logic, I need to tell it, what do I care about? When should this process run? And if I'm designing a clocked circuit, it's always going to care about the clock. If I want an asynchronous reset, meaning that the reset doesn't have to be asserted during a clock rising edge, right? The reset can do it. Then I also care about reset. If reset is not in the sensitivity list, then it means it has to be active at the same time as there's a rising edge of a clock. Otherwise, we won't know that the reset happened. It will just miss it. Then what we're going to do is basically if statements, right? And it's just conditionals. It's just asking questions. And the first question I want with an asynchronous reset is if reset equals 0. Now this makes it an active low reset, right? 0 is reset. Always be careful to make sure that the reset is what you think it is, right? And it's good to be consistent across your designs for the moment. You will run into designs that have kind of mixed resets, which are really annoying to deal with, and I don't ever do it that way, but it could. So this is saying if reset goes to 0, let's reset. And what does reset mean? It means that I want my output Q, and I'm going to start, well, let's just call it Q, and we'll address that issue later. Q gets assigned to 0. There are apostrophes because it's a bit, right? Quotes, or for when it's a vector, a standard logic vector. Many of you, when you define vectors, by the way, are still making the mistake of not defining the size when you declare the signal. Don't forget to say you always have to tell the standard logic vectors how big they are. Don't forget to do that. But here, if we're resetting, let's go to 0. Else if. Well, this is the else if that needs to tell it to care about not just when the clock changes, but when it's a rising edge or falling edge, right? We can do falling edge triggered just as fine. I prefer rising edge. I'm going to most often write RE, but for this sake of review, I'm going to write it correctly, rising edge of CLK clock, right? Just so you know, future, I'm gonna write RE, just as abbreviation. Goodness, these are all like not quite where I want them to be. There we go. Okay, once I have the rising edge of clock, now I can start asking the question, what are J and K doing? Right? That's what I care about. And now I'm going to go through and let's say, all right, well, this is going to be an embedded if statement. We're going to slide it inside. Now, technically, you can put else if rising edge this and something. I really recommend against that. It confuses the logic. So we're going to say if J equals 0 and K equals 0. So this is a logical operator, right? So this is going to generate a 1 or a 0. It's either true or it's not. This is going to generate a 1 or a 0. It's true or not. And then the whole statement with the and will output a final 1 or a 0. It's true or it's false. I don't need that. So that's all this is doing, is it's asking, is this expression true? If it is, then what do we do? Well, Q gets to stay Q. Otherwise, J equals 0 and K equals 1. Then Q gets assigned to 0. Otherwise, right, else if, remembering that there's no space or E in the middle of that else if, which is obnoxious, but it's just the way VHDL is. If J equals 1 and K equals 0, so now we're at the 1, 0 line, Q is 1. Otherwise, I'm going to come up here. Q is not Q, right? Otherwise, else, right? That's the last thing. And now there's a question of why would I want this else? Because I've taken care of every option in this truth table. Why do I want the else?
Throw an error code?
Yeah, I want to know if I've done something wrong. I want my simulation to show me that it's not connected, right? Because right now, if I were to treat this as else, Q equals not Q, well, that would say that in any other condition besides the first 3, we're just going to invert Q. But if my J is undefined, if I didn't connect it, I don't want to invert Q, right? I want to let myself know that I just connected something wrong. So for the sake of you guys, you're going to say Q, it's assigned to, and I don't really care which one you do. I recommend X's because they look bad. I'm sorry. And it has to be a capital X. Normally in our test bench, if we see an X, it usually means dual driven, meaning there's one signal that we're trying to tell to be 2 different values. So that's the one downside that X is, that you're not quite sure why it's an X. It could be dual driven or it could be this case. It's still really easy to check to go see if it's just bad inputs. So I prefer X. You could use some of the other values. You could use U. I would not use Z. Z has some other issues that we'll talk about later. But it's just a sign to say, well, I want to handle all the other cases. The VHDL will not be mad. In fact, there's no problem if there's just an else that. It's okay. It's just harder for you to debug. That's all. Yeah.
The semicolon after the Q, is that still supposed to be there or should be after the X now?
No, they should all, the ends of each of these should all have semicolons. And like this is a then. My syntax on the board is going to be really bad. Just be aware that you're going to have to kind of translate the handwritten code a little bit into real code.
What exactly is the semicolon? Like, is it supposed to be like ending?
A semicolon is the end of a line. Which is a little bit interesting, and it's actually a really good point to bring up. So everybody's going to have to design a mux, right, for the final project. And when we do it, is that a wasp? Yeah. Oh, I hate bees. And I like bees. I hate wasps. Anyways, so the recording people seem to freak out because I got attacked by a wasp. All right. So a mux. So if I have something like m out, the output of the mux, then I need to assign it to something, and that assignment is I'm going to build this. Where to get plots of dots? I'm going to build this mux. I0, I1, MO. Okay, this is the mux that I'm going to build. So the mux is I0 when, oh, I need S for select, right? S equals 0, else I1 when S equals 1, else X. Okay, now this is the exact correct code. I think this would copy and paste in perfectly. Semicolons and everything. Notice that there's not another M is assigned to. It's just M is assigned this when that, else this when that. And notice that there's only one semicolon. That's because technically this is only one line of code. Is I can take this and slot it here and this and then slot it at the end. The problem is it becomes a really long line of code, which is terrible to read and it's horrible for me to help you debug. So we format it like this. We hit a return and then we just tab it in so it all lines up, and it takes me all of 1 second to see what you've done with your code, right? VHDL formatting is not like Python if you've been taking 1400, right? Python is very particular about its spaces and its tabs. Whereas in VHDL, you can kind of throw tabs and spaces wherever you want and it will let you get away with it. However, do this, because when I write instructions in your project that say something like your code is well formatted, if you don't want me to deduct a point, do this, because this is well formatted, because this is readable. Whoa, don't hit it, don't hit it. Don't hit it, that's how you get stung. Blow at it is fine, but hitting it is a bad call.
That scared me.
I don't blame you, but. Okay, let me see if I can kill the bug.
Let's make a machine.
I was hoping it would go away, but
It's just chilling on the window
Yeah.
now. Oh man.
right?
No pressure. 30 minutes. You don't want to.
Can we turn the camera somehow?
We're gonna see him miss.
There's a really big loss. All right. I win.
Good job.
It's mad that it's dead.
Okay. Safety hazard fixed. All right. Anyways, do this. This is a good format. Okay. Here we have a fully functioning, couldn't quite copy and paste, right? This syntax is not all perfect. I'm missing the process that begin. I'm missing the end ifs. So I need an end if for this if statement. And then I need an end if for this if statement. Notice how I'm going to tab my end ifs as well, so that they're going to line up with the if that generated it. Okay, that tabbing will help you. Also, I strongly recommend when you're typing out your code, if you write the word if, hit return a couple of times and write the word end if semicolon, and then go back and fill in the rest of the if logic, because it will help you not run into issues of forgetting that you didn't write the end if, which happens a lot, by the way. It's a silly error. On the exam, when you get an exam, there's going to be VHDL code. I always ask the question, which is basically like, I provide you code that you should be somewhat familiar with, either project one or one of the labs or something that is similar. And I write it, I simulate it, make sure it works. And then I go and I mess it up and I introduce a bunch of errors. And then you get that written out code on your exam. And I ask you to fix the code, find and fix the errors. So for example, on this JK flip-flop, this would be essentially how I would write it, except for I would have the begin. And then I would go and delete the begin, I'd delete the semicolon, I'd tell you that I want an asynchronous reset and I would delete the reset. And then I would give this to you, and I usually successfully say something like, there are 5 errors, find and fix 3 of them. I usually put in at least one more error than I ask you to find and fix. The trick here is making sure that you understand the code enough that you don't start fixing errors that don't exist, right? Because then you think, oh, I got 5, I'm good to go. But if you fix something that's not there, you don't get points for it. So if this were the exam question, it would be, well, here's one. I'm missing the begin. It's supposed to be an asynchronous reset, so it needs to be in the sensitivity list. I'm missing a semicolon here. I'm missing a semicolon here and here. Other good errors, right? I might leave off the apostrophes, or I might turn it into quotes, and then you have to come in and say, no, that's supposed to be quotes. Anyways, that's the type of exam question that you should expect to see in VHDL. The other types are going to be things like giving you this kind of code and asking you, what is this device? Of the devices that I have taught you, what is it? Well, this is easy, right? You'd go, I say easy, people miss this all the time, but if you see there's a J and there's a K, it's probably a JK flip-flop. Be aware that usually I will have like 2 or 3 easy ones, and then I will have other ones where I'll build like a D flip-flop, but instead of calling it D and Q, I'll rename D to L and Q to M, right? And so you have to understand function of code. You have to be able to look at code and think about what it's doing. But you don't have to invent a new device. If I'm asking you what device is this, it's something that you know. Okay. Something that is kind of nice about this course, we had talked about as faculty, splitting this course actually into 2 half courses, essentially, where the first one is digital logic and the second one is VHDL. However, there's an issue, which is that a lot of students that do really poorly in the first half do very well in the second, and a lot that do really well in the first do poor in the second. And the nice thing is that if you're good at one and not the other, as it stands, it kind of averages out, right? If you did really bad the first half and you really well the second half, then it averages out to an A-, and yay, right? So if you didn't understand the first half of this class, if it struggled and it wasn't for you, but you feel confident in the labs, guess what? You're doing okay. It's fine, because we're going to build a lot of VHDL devices, and if that's what you turn out to be comfortable, you're going to do okay. If it turns out that you hate both the first and the second half of this class, and you're going, maybe I don't actually want to be an engineer, guess what? Digital logic is only like one slim sliver of all of electrical engineering, and you'll be able to do other things. You just have to survive the class. And if you're an electrical engineer and not a computer engineer, you can actually avoid this forever if you really wanted to. You can technically take power and set digital systems for the moment. I don't recommend it, but it's an option. Should we do a flip-flop timing diagram just to make sure we're still remember how to do these. I will be posting a homework for timing diagrams with flip-flops today after class, actually. I will post it right after class. Well, between after class and noon roughly is when it will get posted. So let's just pull an example. We're gonna have a J. Okay. Sorry, I'm gonna shift. No, it's okay. Okay. And then we're going to concern ourselves with Q. I can, of course, ask after Q bar as well, but not Q or Q bar is going to just be the opposite of Q. And now let's do one different, actually. Let's do a falling edge trigger device. Let's say the question is, we want to do the timing of a falling edge triggered JK flip-flop with these input waveforms. So the first thing that we do is, if I don't tell you that Q is something to start with, then the answer is, I don't know. In fact, I can't possibly know what Q is until the first falling edge. I don't know what it is. Then I have the next issue of, well, this is 1 and 1, which is a toggle, right? Based on the waveform that I erased, which says that, well, after this falling edge, I'm not X, which is still just, I don't know. And that has to stay true until the next falling edge, which then I'm going to say that this happened just in time for that. And now I have a 0, 0, which is Q, which is more I don't know, right? Because I can't possibly know until I have something like this falling edge. So this falling edge is, well, this one's good, 0, 1. J is 0, K is 1. 0, right? That's reset to 0. This falling edge, 1, 0, it's the reverse, so it's set to 1. This falling edge, I'm going to mark here, we're good. Now we're 1, 1, that's a toggle. Here, this one has no difference. It changes at exactly the same time. What happens when we do that? If we don't know. So the term that we use specifically is it's a race condition, because it is a race between the falling edge of the clock and the falling edge of the signals. So we actually don't know. We have no idea if we're 1, 1 or 0, 0. Or even 1, 0. It could, one of those changes might happen faster than the other one. So the answer is, I have no clue what value I am until this falling edge, when, well, guess what? It's still the same problem. So be aware that if it's happening at the exact same time, there's going to be a problem. And in fact, in general, when I give you questions, I'm going to define terms, if you recall these, like TSU, setup time. And I'll say something like this is 2 nanoseconds, and I'll say there's a T hold, and this is equal to 1 nanosecond. And then I'll give you these timing diagrams, and they'll have timelines across them, like these dashed lines that I'm drawing on my hand. And you'll have to look and see, is this falling edge 2 nanoseconds before one of the input signal changes? That's the setup time. And does it stay the same signal 1 nanosecond for the hold time after the clock changes? The setup and hold times are how we determine if the signal is stable before we clock in the value. Okay. So keep aware, if it's exactly the same time, there's going to be a problem. We're not going to have any clue what it is. The downside of simulators is it will tell you, it will give you an answer. But then you're going to put it on TRPGA and it's not going to work. Worse, it's going to often work sporadically. Like it'll work like 9 out of 10 times, and hunting down those intermittent errors is a nightmare. Okay. There's another cool thing that we can do. So most of this is a review, right? Hopefully from last time. And it's okay. We're actually going to spend time reviewing this again when we come back from spring break, which is next week, right? You guys don't have to put up with me for a whole week and a half now. When we come back from spring break, we're going to review this again, because it turns out that flip-flops confuse people and they're really important. So you're going to see this a couple of times, but we're always going to add on a few new things as I review, okay? So the next thing that we want to do is talk about registers. So a register is just basically an array of D flip-flops, okay? So there's DQ flip-flop. This has the ability to store 1 bit for me. So if I had a vector V, and I declared it as a signal V is a standard logic vector of 3 down to 0. So this is a 4-bit vector, right? That means that this can remember for me V at 0. So I put V in here. There's a rising edge of the clock or fall. If I want this to be falling edge like we just did, there's a bubble. Now it's a falling edge trigger device. Okay. Then the Q will save whatever V at 0 is at the falling edge of the clock. If I want to save V at 1 as well, I can't plug V at 1 into the same flip-flop because that's dual driven, right? That'd be 0 and 1 telling this flip-flop to be 2 different values, which is a problem. So we take another device, we call it D, Q, clock. There we go. Oh. This is now a register. I now have multiple values. It's storing a vector. However, if I have, say, a 8-bit number, this would be really terrible to draw. So what we actually like to do is use buses, right? A bus being a signal that has more than 1 bit within it. And I denote that with the slash, right? The number of bits that are in it. There we go. I now have a 4-bit register. That's all it is. I have to understand that inside of this is really 4 D flip-flops, right? And in fact, an exam question, totally valid, would be to draw this picture and nothing else and ask you, what is the minimum number of NOR gates or NAND gates required to design this device? And you'd have, right, I don't expect you to have that memorized. You go back and look at your notes and be like, okay, well, an SR latch takes 2 NOR gates. Turning that into a D latch takes 2 more NOR gates. So we're up to 4. And then we need 2 of those D latches to make a D flip-flop. So that's now 8 NOR gates. And then I have 4 D flip-flops, so 8 times 4 is 32. There are 32 NOR gates in there, based on the architectures that I've taught you, right? There are other ways to build things, but that would be the answer. Is because I want you to make the connection that this is an abstraction. There are devices inside of this that make up the D flip-flop, and we need to know how they're made. Oh, and before I forget, there is something that I've been seeing that's kind of weird when you guys have been working on this project involving vectors. So this is related. If I have this signal V and I want to assign part of it to a port map, okay? So let's say that I have 2 other blocks of logic, something called U1 and something called U2, 2 different devices. And this one wants to care about part of it. Let's say U1 takes 3 bits of the queue, and this one takes just 1 bit. And we'll say that this one is the MSB, the most significant bit, remember, MSB? So the largest bit in it. So the largest bit is going to U2, the other 3 are going to U1. When I have my port map, so I'm going to have U1 is some device, right? And it has a port map. I need to give the ports a name. A, B. Those could both be port A's, right? Nothing stops me from having the same port names as long as they're not inside the device. Then this would say, well, this is U1, which I've drawn over there. I would say A gets mapped to, if I call the signal Q, which is allowed, right? So V is the input to D, Q is the signal output of port Q. This is fine. It's okay to have different names or same names between the port and the signal that plugs into it. Either way is okay. So what this is saying is that signal Q needs to connect to A, but not all of Q, right? So what I've drawn here is a bus. So what that's saying is Q2 down to 0. Then when I have my port map for U2, whatever device it is, port map B gets mapped to Q at 3. That's how I split a signal. If I want to combine a signal, so let's say that whatever this does then outputs port C, and let's say that C ends up being just 1 bit or whatever. Let's say it's like a comparator, right? It wants to check and see if the value get put in is the right value, and if it puts a 1, it's true. It is the same value, or it's the correct value, and a 0 means it's not. So there's 1 bit coming out of this, and 1 bit coming out of that, and whatever device I have over here, U3, D or E, has a 2-bit input and wants to combine these two. So we split it out into 2 components. Now we're recombining it. Each of these are 1-bit output ports. If I want to do that, well, I cannot do this. This is what we would like to think about doing. U3 is whatever device, port map E gets mapped to, what do I call those? Oh, I haven't given, well, I'll call the signals the same, the D, C. Right, ampersand being the concatenate function, meaning stick the 2 together. VHDL does not like this. It will not let you do this. It will throw an error. So what we have to do is up before the begin, I would have to call like a signal I. And it's going to be a standard logic vector of 1 down to 0, right? 2 bits. And then instead of doing this, I would say, in fact, this, right? I'm not in a process, so this is combinational logic, so the order doesn't matter of what I write. So I come down here, I say, well, I now is, what are there, D and C? And E gets mapped to I. Subtle different, right? I had to create an intermediate signal that was the concatenation. This is 2 bits. Now I can plug the 2-bit I and the 2-bit E. I cannot concatenate at the port. I have to do it at a signal. The next question that kept kind of coming up around the same kind of thing is this is structural code, right? There's 2 options in this, right? There's structural or behavioral. When you create a new design file, it defaults to calling it behavioral, but that's just the name of the architecture. It doesn't actually mean it has to be behavioral. Structural is just a description of how things are connected together. That's what these block diagrams are really good at conveying, is how are these devices connected together? That's structural code. What does it structure, right? Behavioral is whatever is happening inside of these, right? It's doing a comparison. It's asking the question, is A equal to whatever number it's looking for? That's behavioral. So that's the difference between structural and behavioral. So when you're working on your project 1, your top level file is going to be called ALU. The ALU is going to need 5 different component declarations, right? Because you're going to have, well, you can technically do with less, but you're going to have your adder, add with carry, XOR, load and hold, right? So you're gonna have 5 component declarations, sorry, 6, because you're gonna have a mux, right? You're gonna have a 5 input mux with the 3-bit select signal. Do we remember why it's 3-bit select?
It gives you enough options.
Yes, because if there's 5 inputs, 2 to the 3 is 8, which is more than 5, but 2 to the 2 is 4, which is less than 5. So I need 3 bits. That's the minimum number of bits that my select signal can handle. So I have 5 input mux that we're going to write using just a when else statement, right? That's going to have 5 8-bit inputs. Well, 9-bit inputs probably, right? Because your output sum has you have the carry out that you have to deal with. That being said, remember on a carry out, if I have a standard logic vector, it is a sum. The carry out is the biggest bit, right? So if I wanted to do this and combine 2 signals, one of them is a carry out and one of them is the sum. We're calling this result, right? And the output of the mux anyways. CO and sum. So if this is 8 bits, this is 1 bit. This will be 9 bits. And CO will be in the biggest position, the leftmost position. If CO is on the other side, it's in the wrong spot because it's now the least significant bit, the LSB instead of the MSB. So be careful with the order of your concatenation. Okay, new concept, right? I keep talking about devices and whether they are ideal or not, right? Ideal meaning that there's no delay through the logic, there's no gate delay, the setup time is 0, the hold time is 0. That's what ideal means. But circuits are not ideal. And I've been teaching this class, right, from the beginning with the understanding and teaching you guys that it's not ideal. a big part of why these non-idealities matter comes in this form. Is let's say that I need to make a decision based on old data, right? Like a counter. In order to know that my counter, the next number is 5, the last number is 4, right? So what's going to happen is I'm going to take whatever number I'm at now, and I'm going to feed it back into some block. I'm going to call it C. So when we send the output back as an input, we call this feedback. There's a whole bunch of math, like a big reason that you take all the math you do is to understand the math of feedback, which you'll get to in later classes. That's what it is. So this is feedback. It's sending it back to some combinational circuit that is going to help the next round of things make a decision. Okay. So there's an issue is that there's a clock here, right? That is taking whatever is on C and updating it to Q. When it does that, it updates it, it sends it back to C. C then updates this signal. I'm just going to call it alpha for now. I like that as a thing. That alpha gets updated, but it takes a little bit of time, right? Because we're going to design that combinational logic probably with a K-map, because that's what we do the most of. And K-maps tend to end up with a 2 or 3 level of gates, right? 2 if there's no inverts, 3 if there is an invert. And if the clock starts going really fast, then there's not enough time for this combinational logic to update alpha before the next rising edge happens. So it becomes a race. Who wins? Do we get the next value or double clocking the old value? And we don't know. So we have a speed limit because of the speed of our devices, the speed of our combinational devices combined with the setup times is going to determine how fast we can go. Let me explain this equation because there's a new term that I need to introduce. So this is your minimum period, right? Where the period of your clock T is equal to 1 by frequency, where frequency is how many times per second does it happen. The period is what is the separation between 2 rising or 2 falling edges. Now this term we've already talked about, max setup time, which is what is your worst case setup time? Because when you get a data sheet, it's going to tell you like minimum, maximum. You want to account for maximum. What is the worst case situation? So the amount of time maximum expected for your device to set it up, plus the maximum time that you would expect the delay through the combinational logic. Okay, we've talked about both of those. It makes sense that those would be part of the speed limit of your circuit. However, there's a new issue, which is called your clock to Q, which will also be written as clock Q or clock to Q are the most common ways to see this written. Now what the clock to Q is how much time does it take between the rising or falling, but in this case rising, right? There's no bubble, so that means this is a rising edge device. How much time does it take between the rising edge for Q to update alpha? What's the delay? Right? It's the equivalent of the gate delay, but in combinational logic. And in fact, it stems from gate delays, right? Because it's how much time does it take to propagate through those NOR gates. And the more there are, the more complicated the structure, the slower it's going to be. So what this is saying is my clock to Q is rising edge. How long do Q take? So rising edge of the clock happens. And as soon as it happens, our timer has started before the next clock, right? It's now a race to see if we can update. So some amount of time later, Q updates. Then Q gets raced back around to C, and it starts cascading through that logic we designed. And then alpha updates. And then we have another clock coming. We have to ask, did we set that data up in time? Did we make it? Okay. That's how we determine how fast can we run a processor. How fast can our computer go? Is this kind of structure. That makes sense to everyone? Okay. This is going to become really important later because this structure that I just drew up there is very common for digital design. So let's talk then about applications of these flip-flops. And if you recall last time when I talked about JK, I pointed out that if you connect the J and K inputs together at the same to the same input signal, it becomes just what was called a T flip-flop, right? Because it's either staying the same if it's 0 or toggling if it's 1, meaning it changes. So it's called a T flip-flop for toggle. Well, we're going to use this to build one of the most commonly used devices in digital logic, which is a counter. And we're going to call the input to my first flip-flop CE for clock enabled. Is my clock running or not, right? Am I counting? And then I'm obviously going to need another one. In fact, what's funny is this T flip-flop, if the clock enable is 1, every rising edge of a clock, it's going to go 0, 1, 0, 1, 0, 1. Remember this pattern from our truth tables? Remember how we're counting? See this clock enable? If this clock enable is 1 and a rising edge happens, it does this. I've made the first column. I've made a 1-bit counter. Just 1 bit just goes 0, 1, 0, 1, 0, 1. But what you'll notice is that the second column is we toggle every time the output of the first one is 1. So this one is toggling at half the rate of this. So if we say, let's go ahead and update when the other one says 1 in my next one, which is another way of saying and, right? If both of these things are true, which is to say, I want my clock to be enabled and this Q is a 1. Then the only time that this T flip-flop updates its Q is if my clock is enabled and this is a 1, and there's a rising edge of a clock. So if there's a rising edge of a clock and this is 1, we can toggle this column. I now have a 2-bit counter. Well, the third one, the third bit, still T, still Q. Well, it no longer depends on, is this changing, right? It doesn't really care. It's looking at, because we're here, it's looking at, well, essentially, is this 1, 1 is really kind of what it's looking at. And so to do that, we're not going to take the clock enable. We're going to take is at 1, 1, meaning 1, 1. So this one, I haven't drawn this symbol yet. I'm going to introduce it now because you're going to see it. That type of symbol is a port, okay? And its name is going to be Q0. Then this one, I need to feed forward to another AND gate. Because now this is just, am I clock enabled and only one? I have a 1 here, a 1 here, right? Where this is, I keep drawing triangles. Q1. Well, now, if my clock is enabled and I'm 1 and I'm 1, so my clock is turned on and I have 1, 1, this one will toggle. You do. And on and on and on. Right? If I need an 8-bit counter, I can just copy and paste and keep going.
Sorry, what do the ports do in this?
So the ports, this is a very explicit way of saying that my device is going to look like this. It's explicitly saying this is what my output port looks like. It's saying that these signals are going outside of this layer of the hierarchy.
So if you hook those 3 to LEDs, then it just counts as you go.
Yeah, you would see your LEDs counting, which is really quite nice. And the other one, this actually has 2 purposes, because this isn't only a counter. Well, it is, but we can use a counter in a different kind of clever way. So to that point, if you were to hook this up to your FPGA and hook your clock in to these devices, and would you see the LEDs counting?
No.
No. Why?
Too fast.
It's too fast, because the clock on your FPGA is 100 megahertz, which is way too fast for the eye to have any hope of 100 million times a second. No, your eye's not going to see that. But this one's not changing that fast, is it? Because this one turns on and off at the rate of, well, half, right? So that's now 50 megahertz. This is now 25 megahertz. And I do this 8 or 12 more times, and now I'm starting to get into reasonable clock speeds. So this is also what we would call a clock divider. It slows the clock down for us. We can use the output of one of these as a slow clock.
So you could take that and just make a bunch and ignore your other outputs like Q0, Q1, however many, and
Yeah.
just your last one.
And just use your last one as a nice slow clock that we could see as a counter. Yeah. Yeah, and we do this fairly often because we need different clock speeds all the time. And we'll probably come back to counters a little bit more to talk about them in depth because they're kind of interesting, which is this counter has an issue to it. Does anyone know what the issue is?
Does it reset?
Doesn't reset is actually a really good point in that it has to go all the way to 111 before it resets. So we could have little reset pins here and fix it. The issue is speed limit, right? It can only go so fast because this clock enable is what's going to happen is this one will update after 1 clock to Q delay, but this one will update until another clock to Q delay, and this one will update till another clock to Q delay. So let's say that we're at the Q0, Q1, Q2, and we're starting at the 111 state, right? And if I add one more to that, they're all going to toggle, right? And so we're going to go back to 0, 0, 0. So what happens is this one goes, oh, I'm supposed to be 0. And then this one, a little while later, says, oh, I'm supposed to be 0. And this one goes, oh, I'm supposed to be 0. So there's this cascade of delays that start to add up. If
you count over it more than once, then that just gets worse and worse.
Yeah. So eventually the delay between the first bit updating and the last bit updating the last bit won't update until the first bit has already changed to the next number. And you will not even for a moment have the correct number. And it's just going to be this weird oscillating nightmare. So
fix that.
you don't go faster than you're allowed. No, you can do a lot of things to fix it that we'll talk about architecturally, which is if we need to go faster, we build a more complicated circuit. We'll build circuits that don't depend on the previous delay. That's what we would do. But it does add complexity. Yes.
Can't think what they're called. Like your other port, what are you connecting that to? What's
This one?
Yeah.
Clock. If you ever see a wire plugged into this little flag looking port, it's a clock.
Okay.
I should write it explicitly every time, but I'm very bad about that.
And it was when you did that it would run too quickly. The timing of it would.
Eventually, it would become problematic if I cascaded too many of these together. Yes.
So if you don't care about going faster necessarily, but you want to keep it accurate, you can just put buffers in.
Not buffers. The buffers come in. We do need buffers every once in a while. So if I start cascading a whole bunch of these together, eventually this clock signal is not going to be powerful enough to drive. That's what we call it. We won't be powerful enough to drive all of those flip-flops. So eventually we would sever this and put a buffer in. Because now this clock is driving 1, 2 flip-flops and 1 buffer. But this buffer is driving this one. So I haven't added or subtracted anything here, but if I add 4 more flip-flops, it doesn't add to the load of the first one. So buffers do have their place. And in fact, clock management, when you start getting sophisticated designs, which we'll hopefully talk about in digital systems 3610, clock management becomes a big issue to make sure that these types of delays don't add up to problems. There is kind of a fun thing that we can do using this architecture, okay? So let's go ahead and abstract it. I think I have enough time, right? We're 10. So keep this in mind because this is basically what's going to be inside the next block that I draw. Three-bit counter. I'm going to put a U there for unit 3-bit counter because, as some of you have probably figured out by now, and some of you are about to make that mistake, is in VHDL, I'm not allowed to have a number at the beginning of my file names or part names.
Why is that the case? It's really annoying.
It's really annoying, but you're not allowed. It's just how they built it. It's fine. So create your own. This port is going to have a clock enable signal. We're going to have a counter or a clock signal, clock enabled. This turns it on. The clock. We're going to have a 3-bit queue. And we're going to have, as pointed out earlier, it might be desirable, a reset. Active hide this time, no bubble. Okay. I can ask the question now, and you guys, whether you realize it or not, could already answer this. Is design for me a circuit to turn this counter from a 3-bit counter. I only want it to count to 5. How do we do it? Well, what I want, I shouldn't erase this.
Just make the reset true when you get to 5, or?
Yep. So if I want Q to go from 0, 1, 2, 3, 4, 5, I don't want to count to 6, right? Well, that means this is a good reset, right? And we could actually do this with the K-map and saying that this is reset and don't reset, don't reset, don't reset, don't reset, don't reset, don't reset, do reset, don't care. Right? I should never see that. And there's two ways to do this. There's the wrong way and there's the right way. The wrong way will get you lots of points on most of the points on the exam when you get this question, because there will be a question similar to this, which is as simple as doing what you just pointed out, which is saying, well, you were off by 1. You said 5. We want to reset when we get to 6, because otherwise we don't get 5. And we just say, well, this reset then is an AND gate of Q, except for, and if this is Q0 and this is Q2, well, Q0 exactly has an inverter.
So why is that wrong?
Because it's not the simplest circuit. Because, and I don't even need a K-map for this one to do. However, the more sophisticated ones you might, which is to say, well, see how there's a 1 and 1 here? This is the first time that it happens. That 0 doesn't matter. It is literally Q1 and Q2 if this happens. So I can just erase that line.
So if you only wanted to count to 3, then you could just say, connect your reset right to Q2.
Yes, exactly. If we only wanted to count to 1, we wanted to go 0, 1, 0, 1, because we'll reset as soon as here.
No, if you want to count to 3, then you connect it to Q2.
Oh, to Q2, yes. Yeah, if I only want to count to 3 and I want to reset here, then it would just be a Q3 feedback to the reset.
So if you wanted a simple reset on a counter that would count to 8, then you could just add a Q4 and reset as soon as it was 1.
Yep. If you had a 4-bit counter and you needed a 3-bit counter, that's what you would do. Anyways, these feedback type of circuits that help you make the decision, they look exact, right? This is all I did. It's just that the C block is 1 gate. See this input? This might be an option, right? This might be and enable. Maybe sometimes I want to count to 7 and sometimes I want to count all the way, or 5, and sometimes I want to count all the way to 7. So now my enable is 0. That's now enabled. As I have.
Yeah, I was just gonna say, so for the 3-bit counter, how would you move that up? So let's say like LEDs or something from there.
So this is 3 bits.
So just from right there.
Each of these, LED, and to repeat. Right, where this is 1 bit, 1 pin as mapped on your FPGA through a constraint file. Anyways, that's 10:15. You guys are free to go. I'll hang out for a little while afterwards if you want to ask questions.
So I was just trying, so you have Q2 just feeding into both inputs of the end.
This, no, I was trying to simplify the drawing that I drew too small. So here we're 2, here we're splitting out to 1 and 1, where this is Q1 and this is Q2.
And we just don't care about Q0 in this instance.
It doesn't matter. And we could do that. We would find that out through the K-map because of these this don't pair and that one are going to be logically adjacent. So they're going to share an implicant, which means they're going to, if I have a circle that encompasses 2, it drops 1 variable, and the variable that will be dropped is Q0. But as I said, we're going to be using K-maps as this logic gets more and more complicated. As it stands, I just don't need it, but you would get the right answer with the K-map from this truth table.
I have a question about college in general.
Yeah, let me hit stop on this.